technologies are used. One is vacuum tube type and one is solid state type. And if you are going for a solid state type, BJT is the example. And if you are going for a vacuum tube type, then triode is the example. So triode, if you see, this is developed by J. Fleming. Triode developed by LD Forest. Similarly, if I'm going for four type of electrodes, so that is known as tetrode, pentode. So these are devices, all are developed under vacuum tube technologies. But due to bulky in nature, those are not popularly used. So semiconductor-based devices are popularly used. And in first transistor, if you have seen in 1947, it was developed. So all the three names already I told. This is Shockley, Bratton, and Bardeen. They have developed the first transistor in BELE laboratories in USA. So this part already I told difference between advantages of solid state technology over vacuum tube technologies. So it is not required to once again to repeat that. Now coming to transistors. Now what are the types of transistor? So first is based upon the what type of material you are using or what type of semiconductor you are using. Based upon that, your transistors are categorized. One is germanium, silicon based, gallium arsenide based, silicon carbide. These are the semiconductors are used to design transistors. Nowadays, popularly carbon, graphene, and gallium nitride also popularly used. Am I audible to everyone? Hello.
Yes, sir.
Yes, sir, you're audible.
Okay. So this is a semiconductor material what you're using. Based upon that, transistor are categorized. So first you remember here, germanium first semiconductor is used to develop the transistor, then silicon. Now people are working using graphene and gallium nitride. Now if you go for structure based, already BJT and FET. So BJT, bipolar junction transistor, FET. FET is a field effect transistor. Under field effect transistor, there are different types like gate field effect transistor, metal oxide semiconductor field effect transistors. So MOSFET type of devices you heard about that. So that is coming under FET, field effect transistors. So these are the structure point of view. Structure point of view means how or what semiconductors you are designing, or you can see I'll tell you the structure point of view also. So how your semiconductor you are putting and you are using as three different terminals, based upon that you can categorize. So in BJT, if you structure wise, if you see in BJT, we are the terminals are known as emitter base collector. In case of FET, we are naming as drain source gate. Now, based upon the electrical polarity, so transistors are two types. If you go for BJT, it is NPN and PNP. And if you're going for FET case, that is N channel FET and P channel FET. And maximum power rating is low, medium, high, because power rating means already I told in diode also power dissipation, VD into ID. So power dissipation, depending upon that, transistors also named as low power rating or medium power rating or high power rating transistors. So depending upon the frequency range also they are categorized. One is low frequency range, medium frequency range, high frequency range or radio frequency range, and micro frequency range. So depending upon frequency range, the device is developed that those transistors are named as low frequency, high frequency, and micro frequency transistors. Application already told, switch and amplifiers. And in terms of packaging also, there are different packaging standards are used, like through-hole metal packaging, through-hole plastic packaging, surface mount, ball grid array, power modules. So depending upon packaging also, transistors are classified. Now, in terms of amplification factor, already you have seen beta, already I told, so beta or HFE in case of in case of BJT, and GM is transconductance, which is depending upon, or this feature we are observing in FET. So these are the amplification factor means output by input. In case of BJT, you can see IC by IB is known as beta value. IC means collector current divided by base current. If I'm taking a common emitter configuration, so this is your amplification factor beta. In case of transconductance means a change in current divided by change in voltage. So that is known as transconductance. That feature we are calculating in case of FET. So these are the transistors classification based upon different uh, characteristics. These are classified. Any doubt in this case? Any queries?
Can you please define transconductance once again?
Transconductance, you can see beta bit. Wait, point. So beta, wait, what the marker? Okay. So in beta, if you can see beta in a BJT, it is a three-terminal device. One is base, emitter, and collector. So there you are calculating the ratio of output current divided by input current. So if I'm taking one configuration is known as common emitter configuration. I'll let you know later on. So common emitter configuration, if you see output is IC current, means collector current, divided by input current IB. So if I'm taking the ratio of that output by input, that is known as beta. And HFE means this is hybrid parameter, same thing, because when you are taking equivalent circuit diagram of transistor, if I'm using hybrid model, so based upon that, H is referred. F means F means this is forward. You can see E for emitter. So that beta and HFE both are same. So if you want to find out output by input, so that means change in output current divided by change in input voltage. That is known as transconductance. Okay, so that
Okay,
feature we have to extract in case of FET. So similarly, if you see VI characteristic in diode, similarly VI characteristic of transistor we will consider. Okay, so whenever you are plotting the output characteristic, there you can find out change in output current, it means drain current, divided by what is your change in input voltage.
Yes, sir. Thank you.
Now, types. If you go for BJT, these are the recently most popularly we are using. All are bipolar junction transistor. Bipolar means both electrons and holes are responsible for flow of current. So that's why it is known as bipolar. Both electron and holes are responsible. Similarly, in FET, it is known as unipolar device. So only either electron or hole will be responsible for that. So in BJT, if you see SBT, IGBT, HEMT, these are the transistors based upon different doping level or different doping level, they are categorized. FET also you can see MESFET, MOSFET and OFET. What type of material also you are using, that is very important. So here MESFET is metal. You can see all full form I have written. You can see here. MESFET is metal semiconductor field effect transistor. MOSFET is metal oxide semiconductor because you are using silicon dioxide to increase the input impedance. So that's why it is known as MOSFET. OFET means organic field effect transistor because people are now designing instead of semiconductors, now they are using organic materials as as the material to design the transistor. So that is OFET, organic field effect transistor. So these are the different types of transistors based upon what type of semiconductors or what type of materials you are using, that is named as.
Sir, can you please explain why we call it FET as unipolar?
So either you can see already I told because all these devices are developed using semiconductors. So either P type, N type or both P type, N type you can see. So their carriers or majority carriers are in case of N type electrons and P type holes. Now if you're using both type of semiconductor, now in some particular configuration, you can see electrons and holes are responsible for flow of current, that is BJT. In case of FET, either only one, either electron you can take or hole you can take. How it is happening? Because depending how you are taking the semiconductor. So whenever we will go for the structure point of view, this point will be more clarified. But if for the time being, you can remember only either electrons or holes are responsible to flow the current. So that's what is known as unipolar device. Okay, now first, as I told, BJT part we'll discuss, then we'll go for FET part. So BJT, now we'll see the construction point of view. So if you see the diagram, I told there will be two types of BJT. One is NPN or PNP. So here you can see in transistor, there will be two PN junction I told. So to create two PN junction, either you have to take two N-type semiconductor and one P-type semiconductor, or two P-type semiconductor, one N-type semiconductor. So depending upon how many number of P-type, N-type you are selecting, so based upon that we can classify either it can be NPN or PNP transistors. I hope it is clear. So two N-type semiconductor you have to consider, one P-type semiconductor, then it is NPN. If I'm taking two P-type semiconductor and one N-type semiconductor, then PNP transistors. But for the cases, you have to create two PN junction. Okay. So now, for example, I'm taking any one configuration, either NPN or PNP. So you can see three terminals are there. So here you can see three mark I have given. So this one, or this one, or this one. So three terminal device means you can see there are three. The terminals are named as emitter, base, collector. So first one is emitter, middle one is base, third one is collector. Similarly here, emitter, base, this is collector. Now what is emitter? Emitter, if you see the name emitter, so it emits the electrons. If I'm taking N type, it will emit electrons. If I'm taking P, here emit will be holes. So here majority will be electrons, here majority will be holes. So which one is emitting? So that is emitter. Which one you are collecting? At the end you are collecting, that's what is collector. And P base is the in between emitter and collector. So by you don't have to mug up, by knowing his name, you can remember the definition. Now I told, now to create more electrons, so doping is very important, already you know. So to create more carriers, so then your emitter should be highly doped, and collector will be moderately doped, and base is lightly doped. So these are the features of three terminal transistor devices, and you can remember this nomenclature. So if once again, if you go for definition wise, this is a 3-layer semiconductor device consisting of either 2N and 1P type of layers of materials, or 2P and 1N type of layer of materials. So based upon that, NPN and PNP transistors are classified. This point are clear, or any queries?
Sir, why the collector needs to be, why the base needs to be lightly doped?
Now you can see, because you have three options. One is emitter, because we have to generate more electrons or more holes, so that's why it is highly doped. Now we have to base. Base is very you can see dimensional wise also it is thinner, very narrow, because it will create PN. You can see barrier potential will be created here only and here only, because PN junction is there. So now depending upon biasing, this region or this barrier will be controlled. So that's why this is the path where if I will take electrons here, so electrons will flow from this path to collector only. Now controlling the electrons or carriers, you can control the current. So in this type of device, if you see, I can take current also based upon that. This current, whatever flowing is IC, this is IB, and this is IE. So if you see, always total, if you apply the Kirchhoff's current law also, IE is equal to IB plus IC. So now to this feature we have to, or this rule we have to follow in this type of devices. So to control this current, so accordingly also you have to dope. So based upon that, you can see emitter will be higher, so that's why it is highly doped. IB and IC, if you see, IC is collector collector current, it is moderately doped. Base will be automatically less, because IE is equal to IB plus IC. And in transistor device, you can see IB will be very smaller. So if you see, more of only we are taking IE is equal to IC. So to make this type of concept, IB automatically should be lightly doped.
Yes, sir.
Okay, now coming to your point. So construction wise also you can see NPN. So here this biasing voltage, for the time being you may you don't have to remember here. I will tell you the logic behind that. So first, if you take, this is emitter, this is base, this is collector, and emitter is highly doped compared to collector. So that's why you can see, and also you can see approximately, if you see this width are approximately same or little bit higher than collector to satisfy this condition. Now once you create or you are taking the NPN configuration, now already I told biasing is required to overcome the barrier potential, because two PN junction will be created here. So based upon that, you have to give the biasing voltage. So here you can see, always here it will be always in forward biased input. This is your input, this is your input, and this is your output. So already I told here, to make the device efficiently operate, so your input loop, or you can say emitter base loop, will be forward biased always. Similarly, for output loop, means base and collector, that will be always reverse biased. You may have the question why? Because this device we are operating as amplifier. Because if you are taking this forward bias and reverse bias, so it will create, or this device will be in active region. So when we will plot the VI characteristic, at that time we will once again I will repeat there. So this device will be operating active region. Active region means your amplification factor will be a constant or it will amplify. So that's why this transistor to operate as an amplifier and biasing is a requirement. So to give proper biasing, input loop always be forward biased and output loop should be reverse biased. And here you can see input is emitter and base and output will be base and collector. Is it clear for NPN transistor? Similarly, PNP transistor also same thing.
Is this condition for amplifier?
Amplifier only.
Okay, sir.
So that the picture once again we will draw the VI characteristic. At that time once again I'll repeat it. Okay.
Sir, you told that BJT is of vacuum type, but this is of semiconductor type, no?
No, we are discussing about semiconductor type now because vacuum type technology is also used, but we are not following because this is bulky, costly. So that's why we are not using that vacuum tube technology. In vacuum tube technology, that transistor is known as triode. Are you getting me?
Yes, sir.
So in your syllabus, all are semiconductor based technology we are discussing, or solid state technology we are discussing. Okay.
Okay, sir.
So here also you can see in PNP it is also forward biased. You can see the biasing also forward biased and it is reverse bias. So forward biased you can see P is connected to positive, N is connected to negative. Okay, so this is construction wise I told, and biasing part also once again I will repeat later on. This is for construction wise NPN or PNP transistor. Okay, any queries? So whatever I told, emitter layer is heavily doped and base and collector only lightly doped. So this part already I told, this is not required to discuss once again. Now we will go for the operation of what I told. Once again we will discuss operation point of view or working principle of PNP transistor. So you can consider NPN and PNP. Once one you understood, other one will be also simpler. Now if I'm taking PNP transistor and what I told, input will be forward biased and your output loop will be reverse biased. So then what is happening? We'll see. So this the now first point you can see during this forward bias condition, what will happen? So this voltage you are giving, now already you have seen PN type, PN junction is there. So now during forward bias condition, what will happen? So this depletion region will be thinner. You can see depletion region will be thinner because already we have seen in PN junction diode, the junction layer will be reduced when it is forward biased, and reverse biased it will be widened. So for this case you can see forward biased will be applied here. So this junction layer will be thinner. Then what are the majority carriers in this P type of semiconductor? So these holes you can see it will flow from emitter to base, because this is, you can see it is providing low resistance path due to thinner depletion region is created due to forward bias condition. Clear?
Yes, sir.
Yes, sir.
Similarly, in reverse bias condition, what will happen? You can see this second PN junction will be thicker. Are you getting me? Second junction will be thicker due to reverse bias condition. Now due to reverse bias condition, now already I told in reverse bias condition there is a small leakage current or flow of magnetic carriers will be. Also some magnetic currents will be flow. Now, if you go for total current, so total current will be what? So total current, we can current. So total majority, or I can write I majority plus I. Sometimes it is very less. Already I told in leakage current it will be less. So only whatever current is flown from emitter to collector, it is due to only majority carriers. Okay. So it is P type. So current will be flown like this because whole majority carriers here. So current will flow from this direction to this direction. So I can write IE. Okay. So this is your IB and this is your IC. So this is not here. So here I have to write. This is not right because this is only I have considered forward bias condition. So here I can consider. So this is my IE. This is IB. So now total current, if I will apply, because I'm taking this 3-terminal device here. So this part you can see. If I'm taking this is base, this is emitter, this is collector, and if I'm applying the Kirchhoff's law here, so IE is equal to IB plus IC. So applying the Kirchhoff's law at this node at base, so then your emitter current is equal to base current plus collector current. And already I told this IB is thinner, so IB is very smaller one, which is you can see this is in microampere, and IC and IE will be in milliampere. So based upon this condition, because IB is very smaller compared to your IC, so then we can write IE is also approximately equal to your IC. So based upon this condition, we can write IE is approximately equal to IC, as IB is equal to a very smaller, which is in microampere. Okay, so once again, this combination of previous two diagram, previous forward bias and reverse bias condition. So here you can see thinner depletion region, here is wider region. Now you can see currents which are majority carrier currents which are flowing due to this forward bias junction, and due to reverse bias junction, this magnetic currents will be there. So now total IC, the total collector current is equal to what is the majority carriers current and due to minority carrier currents. IC is equal to I majority plus I minority. So here we can write approximately equal to depends upon I majority, because leakage current will be very minor one. So sometime we can write IC is equal to I majority current due to majority carriers. And symbol point of view, you can see the device, this is all construction based. Now in circuit diagram, or whenever you are designing a block diagram of any system, and you want to represent your transistor in symbol based, so this is the symbol you can see for PNP transistor. So PNP. Now you can see you don't have to mug up. Now current direction you can see P to N. So that's why you can see current is shown P to N. So you can see arrow diagram you can make P to N. So here you can see this symbolic representation of PNP transistor. And I is equal to IB plus IC. See each part of the diagram and let me know any confusion, anything is there, let me know.
Sir,
So
how
this
are the holes from the emitter region are moving to the collector region? There is a thick depletion layer here. So how are they crossing the base and moving to the collector region?
Means when how the question is a little bit tricky. How because this is the device properties. So here you can see. So whenever you are making this, because this carriers where it will go. For example, this when emitter is creating the carriers, it should flow to some place. So that's why this device doping level is managed such a way that it will be carriers will be collected at the collector only, and only we have to see in collector what are the carriers are you are obtaining, because due to majority carriers also you are getting, and also minority carriers you are obtaining. And due to this majority carriers, current will be there, and minority carriers current will be there. So the naming is ICO, it is written, and majority is IC is mentioned here. And total collector current you can see based upon the carriers level. So IC majority and ICO minority. But how it is happening, because you have to go in physics level, then how many carriers are you are obtaining. For example, this number of carriers are created, and how many carriers you are obtaining at the collector end, and what are the other number of carriers are there which are not able to cross the barrier potential. That everything you have to that part may be clarified in the physics part. If it is you are more interested, you can refer those books also.
Okay, sir. Thank you.
Now, now what we are dealing with, because we are observing that this type of features, and these features how you are implementing in circuit design, that part we will discuss in this subject. Okay, so for the timing, you have to see what is your IC current we can write due to majority current, majority carriers. What is the current you are achieving, which are approximately, or you can see this is maximum current you are obtaining, and ICO, which is leakage current or reverse saturation current, you can say, which is minimum. Both the combined or both the factors which are depending upon or which is calculating your total collector current. Now, if I am taking a as a node point, so here if you see total I is equal to IB plus IC, and this device this condition always satisfied. Either you can take PNP or NPN. So similarly, NPN case also same process you can follow. NPN, because N you can see N more electrons here. N majority carriers are electrons, so electrons are flown in this direction. Current will flow in opposite to that. So remember here electrons are flown here, and current will be opposite to this. So that's why you can see I is equal to IB plus IC. So this current direction will change. So IC will be this one, IB will be this one, and I will be in this direction. So same thing here, when you are going for combining both forward bias and reverse bias. So majority carriers, you can see here electrons, you can see it is flown from here to here. And in case of device, if you see a symbol presentation of your NPN, so current direction you can see not below, PNP is below, and NPN you can see opposite to that. So that's why IE, IB, IC. So in PNP, how it is there? I am once again drawing it here for your reference. So emitter, base, this is collector. Now here you can see current will be like this. So this is IE, this is IB, this is IC. So this is PNP. So this difference you have to remember. So current direction will be here. So this is PNP. So only difference between NPN and PNP, the flow of current direction. And also biasing is you can see input is forward biased and output will be reverse biased. So these three condition you have to remember. Once again I'm repeating. One is biasing, input loop or emitter base loop is forward biased, output loop will be reverse biased, and applying the Kirchhoff's law at the node, so you will get IE is equal to IB plus IC. So this is about construction type. Now we'll go for configuration wise. Transistors are three types of configuration. Now already you have seen in a transistor how many terminals are there. So three terminals are there. So emitter, collector, base. So here in this configuration you can see base is common to emitter and collector. So based upon that configuration, if you see common base, common emitter and common collector. So what is the difference between them? Because here you can see common base. So if I'm taking like this, if I'm taking here, so this is base, this is emitter I'm taking, and this is collector. Now here you can see emitter is common. Now here you can see this is common emitter configuration. This is common base configuration. So common base configuration means base is common to both input to output. Now this is your input and this is your output. Now this is your input and this is your output. Now based upon the terminal which is common to both, so the transistor we can classify either common base, common emitter or common collector. So if I'm taking similarly collector also, then C will be common. So now we can take same thing, like you can see this is collector. So this is this is base and this is emitter. So common collector also we can discuss. So most popularly common base and common emitter are used for amplifiers, because here input impedance and output impedance based upon their common base and common emitter are popularly used for amplifiers, but common collectors are used for impedance matching devices, or we can see emitter follower. I will later I will brief you the application emitter follower. It is act as emitter follower. So this three configuration what I told: common base, common emitter, common collector. So here also I've written common base and common emitter is known as act as amplifiers, and common collector acts or used as a impedance matching device. So in input impedance matching device, if you see, so different input impedance, or you can see two devices are there. One is Z1, one is Z2. So one impedance is 50 ohm, one is 100 ohm. So in between, if you want to design a device which is input is matching to 50 ohm, output is matching to 100 ohm. So that type of device is known as impedance matching device. So this common collector configuration can be used as impedance matching device. Whenever two different impedance levels are there, so you can use a common collector transistor configuration to match between two different impedances. So that's why common collector is used for that type of applications.
Can you repeat why common collector is used for impedance matching?
So already I told if for example, for a particular application, now you can see two different impedance levels are there. So one, for example, Z1 I have taken 50 ohm, and Z2 I have taken 100 ohm. Now already you know for communication purpose or any signal you want to transfer from one impedance level to other impedance level. So maximum power transfer can happen when both impedance are matched. Okay, but in this case, if I'm taking an example 50 ohm and 100 ohm different impedance level, then whenever I'm sending or passing a signal, so that signal may not reach the 100 ohm impedance level due to mismatches of impedance. So that's why we need another device or another network which will give you a transition impedance level in between them. So this common collector configuration which is providing this features. Why? Because input and output impedance are different for common collector configuration. So that that feature we can utilize for impedance matching purposes. Now here if you see three configuration I told, common base this is common base configuration, already last one we have discussed. So here you can see base is common to both input and output. So that's why it is known as common base configuration. So now in common base configuration,
Sir,
we
in
have to
common base configuration, you said it is amplifier. It is used for amplifier. Sir, where
yes,
the which is amplifying current or voltage? What?
current, because this BJT I told this is a current control device, so current is amplified, so IC will be more based upon that we are getting current. Here you can see what is the amplification factor. Once you know, then it will be more easier to understand that. So here now this is because this is, you can see we are not using any load other thing we have to use for a better amplification. Okay, for the current scenario based upon the construction point of view I am telling, so this is common base configuration because base is common to both input emitter and collector. So that's why it is known as common base configuration. Okay, so here we'll see what so now amplification, when I will see, when I will go for input and output feature I will draw, then I will get it. Okay, so now here you can see for input loop, so here you can see input loop here and this is your output loop. Now already you told I am telling this amplifier or something else, so first we have to draw its characteristics. Characteristics means we have to plot voltage and current. What is the behavior of voltage and current at the input port, and what is the behavior of voltage and current at the output port. So first you can see here for input loop, so what current you can see, this is common base, so you have to see so this is, you can see what input loop you have to see here. Now in input feature, so what is the, you can see this is biasing voltage and this is the current, you can see this is your input current IE and this is IV. So we have to see the behavior between voltage and current. So here this is your input loop, input, or we can see input characteristic. Input characteristics means what is the input voltage here? So you have taken VE. VE means because it is connected to emitter and this is connected to base. Either I can take VE or I can also take VBE. Same thing. Because voltage across two terminals, we can write VEE or VBE. So now this voltage versus current. Current is because based upon how much voltage you are giving, based upon that your emitter will emit the electrons. Now based upon the electrons, this current will control IE. So that's why input characteristic you can plot between the voltage and the current. You can see if I'm changing the voltage here, based upon that current I will get it. So that's why this is input characteristic for common base configuration. The plot is in between IE versus VB. And you can see this is, if you see why this type of feature is we are getting, practically also you will get it, because it acts as a p-n junction diode. So it acts as a p-n junction diode. So p-n junction diode, you can see this is p-n junction diode. So in p-n junction diode, after the barrier potential, current will increase. So that voltage is no knee voltage. So now for silicon or what type of transistor you are taking, but based upon that, this current will flow. And and you can see here three parameters are there. One is input voltage, one is current, and one is input current. Now you can plot for different input base level, you can plot this characteristic. So this plot will be like this, because once again I'm repeating here. So here once again I'm plotting. So this is your voltage emitter. What is the voltage you are giving, and this is your I. So for particular for particular input current, so if I'm taking particular IB values, at particular IB values I'm varying this voltage. Now for each voltage, now I will get different I. So if we plot, I will be like this at a particular IB1 values. Now if I'm taking silicon, so after 0.7 volt it will increase. Now if I'm varying this base current, different IB values, so similarly I will get different values, but it will behave like this, because after various potential or knee voltage, current will increase, because you can see here input loop is based upon the p-n junction diode. Clear? Any queries? Hello, am I audible to everyone?
Yes, sir.
So,
Yes, sir.
I have question once again.
So because you can see this input, you can see this is your input loop, whatever mark I have given here. So this is your p-n junction diode, and this voltage you can see this is given in bias. Okay. Now at different IV values, because whenever I'm connecting some in this branch, now what's IE? So Pn, because current will flow like this, because electrons will flow like this, and current will flow like this. Because why electron? Because n type of semiconductor here, so it is electron will emit, so current will flow in this direction. Now IB, because at different IB levels, because whenever I'm giving some supply voltage, so current will also vary. Na? That feature we have to draw. So for a particular IB value, when I'm varying this voltage, so I will be behaving like this. And why it is behaving like this? Because it is similar to your p-n junction diode. So that's why after knee voltage it is increasing. And I'm changing the IB values. So similarly I'll get this type of behavior. So this is the input features of your common base configuration. Similarly, if I go for output, so IC, you can see IC versus VCC. Okay, so IC versus VCC, you have to plot VCC or VCB, because the voltage which is connected between collector to base, we can write VCB or VCC. So we can see here. So this behavior we'll see here. Once again, I'm showing the actual diagram which is given in your book. So this is your input characteristic. So only here you remember what are the variables we are using based upon that characteristic. Okay. Similarly, if you are going for output features, so this is your output characteristic. So here a different voltages, common base, collector base voltages, your output current will be varied, and at different IB values. Because input current you are giving, so at different IB values you will see. So don't worry, this part I will explain once again because this is already written previously. So once again I will do it for you for clarification. Whatever I am telling, please go through the book. You only study the basic about the transistor part, and this common base configuration I will start once again in next class. Only you go through the book and see, read once again, and next class I will repeat this part, common base configuration. Once you are clear on this, in all configuration you have to see input and output features. Now don't worry about this. This is a natural feature, or you can see this plot will be a any device or any transistor you are designing. So this behavior you will get. So already I told active region means this is your active region. This is your active region. Here you can see your amplification is a constant factor. And here you are giving biasing is forward bias and reverse bias. Whenever you are giving both reverse bias or forward bias, that depending upon cutoff region and saturation region will be created. Okay, so next class we will discuss more detail on that. You may have other class then. Okay, so you can leave, already 3 minutes late. Next time once again I will repeat it. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.